Welcome back everyone. Today we're going to be talking about how to control the power going into a TEC. Now of course you'd have a positive and a negative, and if you've ever applied a voltage to it, it uses the voltage, creates a temperature differential, and hey presto, it's all working. However, you may find that, hang on, it's a bit too cold, it's a bit too hot, I haven't got quite the correct input voltage, how do I convert that? How do I control the power going to a TEC? So we're going to talk about how to control the power. We're not going to talk about how to control the power based on temperature, although at least one of these actually will do that. So if you look on AliExpress, eBay, Amazon, you'll find a whole bunch of different terms and potential methods for controlling TEC power, and we'd all like to know what can be used, what can't be used. So there's two basic ways of controlling power to a DC load like a Peltier, and that is either through voltage or through current. And we're going to start with the voltage ones and then move on to the current ones. So you'll find that on the internet there's a whole lot of boost controllers, which people will call step-up controllers, and you'll find there are buck controllers, which are step-down controllers, and buck boost, which is, you could say neither because they cancel each other out. However, they can buck and boost depending on your input voltage. So a boost controller will take, say, a 5 volts in and will boost that up to whatever voltage you want, say 12 volts. And you can adjust the trim pot, which is here, to adjust the output. Now, for controlling TECs, that implies that you have a lower input voltage than output voltage that you want. So say you've got, like I said, 5 volts input and you want it to be 6 volts. Now that obviously means that your input voltage has to be lower, but it also means you can't turn this TEC off with this, because all you're doing is taking the input voltage from a lower value and boosting it up to a higher value. So you have no way of actually stopping it. It's just a way of increasing the voltage. Now this could be quite good if you want to increase the voltage because you've got, say, a 24 volt TEC and you've only got a 12 volt input power. So you can then adjust that from approximately 12 to 24 volts, or half the power of the TEC, but you can't turn it off. And a buck is pretty much the inverse of that. So we've got a 12 volt power supply, we can reduce the voltage down to theoretically 0. However, an awful lot of controllers cannot actually reduce the voltage down to 0, so that's something to be aware of too. So you may not be able to adjust it and prevent any current from flowing in, slash voltage, or power if you like. But these are pretty jolly useful. You'll be probably powering it from a car or from a PC power supply. You want to control your 12 volt-ish TEC. You can then just turn the trim pot to adjust your output voltage, which will relate to a temperature. So these are highly practical, but be aware that you may not be able to actually stop all of the power going to the TEC unless it can go to 0. However, you may say if it goes to 0.8, the amount of power it's going to be drawing so small that it's not a big deal, and you'll always want more than 0. Moving on to the buck boost. Buck boost does the same as the buck and the boost controller, but combined in one. So let's say you've got a 24 volt TEC, 24 volt one, and you've got a 12 volt input voltage. This will then boost this to 24 volts. Obviously you can adjust the output voltage, but let's just say 24. Now the cool thing about a buck controller is what happens if the power drops. So if the power drops down to 10 volts, it'll still boost it up just like the boost controller. If your input voltage increases, say your input voltage is now 32 volts, but you still want that output voltage to be 24 volts, then the it's supposed to be a 4, then the buck boost will then reduce the voltage down to 24. So that's really flexible if you have a really wildly variable input voltage and you want a constant output. So this can handle, say, 0 to 32 volts, and it will always output a 24 volt power supply. Whereas these other systems can only do one or the other. They can only increase the voltage or decrease the voltage. So now we move on to good old-fashioned voltage regulators, which look like MOSFETs, and they are pretty much normally a static voltage, as in you buy a 5 volt one, so you apply whatever voltage to it and it outputs 5 volts regardless of input voltage within reason. Now these are of course seemingly simple, except all of the difference in the voltage, to say you want to reduce 24 volts down to 12, will result in the rest being burnt off as heat. Now in the world of TECs, when we're talking about 20 amps, 10 amps, 5 amps, that equals a fire. So while these are quite cool / usable for very low wattages, TECs, no. We're going to now move over to current, which basically how the current limiters work is they just turn the switch on and off, on and off, on and off at varying rates. And that adjusts the power going to the TEC by its average. So if it's on for 1 second and off for 1 second, off for 1 second and on for 1 second, that is 50% of the power, and that's PWM. Okay, so the easiest way you could say of controlling a TEC is with a PID controller, which looks like this. They've normally got wonderful LCD screens, and you can set the temperature and it will turn a relay on and off based on the temperatures you've set. Now this might seem like a truly wonderful solution, and we're all going to rush out and buy PIDs because that's the simplest way of doing it. However, this is ultimately one of the worst ways you can possibly control a TEC. So please don't control TECs with PID controllers. There may be some PID controllers which are not going to be covered by this generalization, but in general you set a temperature of, say, the TEC coming on at 27.1, I guess, and turning off at, say, 25 degrees. Now that difference in temperature will result in there being quite a delay with the difference between when the TEC is on and when the TEC is off. Now that means that the TEC will be off for, say, 30 seconds and then back on for 30 seconds and then back off for 30 seconds and then back on, or potentially even greater, especially if you're doing like water to water cooling. You may find that it'll be on for a minute, off for 2 minutes, back on for 2 minutes, or whatever. Now if you've ever watched my video on TEC reliability, the TEC is capable of transferring heat even with the TEC off. TEC is dissimilar metals glued together. Metals conduct heat. So with the TEC off, it will conduct heat. So normally you'll have your heat load here. It's rejecting heat. And you normally want to move that from one side to the other. However, when you turn the power off, if there's a large delay between the power being on and off, it'll just transfer the heat back through the TEC in the opposite direction. And then when it comes back on, it'll move it back up. Turns it back off, it'll transfer it back. Now, as you can imagine, this is a horrible way of being efficient if you're transferring a heat load to one side, turning it off, letting it leak back the other way, and then turning it back on and moving your heat load plus the amount of heat that you've leaked back the opposite direction. It becomes quite a thermal runaway. Now obviously the thermal resistance, or how well the TEC conducts heat when it's off, is not particularly great, but if you have a large temperature difference, you'll find that it will quite conduct the heat back. So much so that in thermoelectrically cooled computers at idle, you probably don't even need to have your TEC on and your computer will be stable, and that's what I have done in the past. You can just turn your TEC off. Yes, your CPU loads will be hotter, but it won't be so hot that it will destroy your computer, because um, at idle your computer doesn't use very much power, so it can work without the TEC on. So using a very, very slow frequency pulse width, you could say, this is a vague pulse width, controller like a PID is very bad for overall efficiency. And you can also say that this will result in significant thermal flux across the TEC, or heating and cooling of the TEC, which will increase the stress on the TEC by heating it up, it's expanding, and then cooling down, it's contracting, heating up, it's expanding, cooling down, it's contracting. So the TEC should last a lot shorter, be less reliable if you use a controller like this. But that is the easiest way to control it. It's out of the box, you've got a little nice screen, you can program it up, plug your SSR in, and you're all done. Now, moving on to possibly the completely opposite of the all-in-one solution PID controller, to the MOSFET. And the MOSFET is just really basic. You've got 3 wires and you have to connect one up to something like an Arduino. And you can use the Arduino to PWM the MOSFET, which will then limit the power going to your TEC. Now this is the simplest way of doing it. However, there are some caveats. If you're going to be using an Arduino, which is 5 volts output, to control a MOSFET, the MOSFET has to be able to open the gate or open the switch, because that's pretty much what it is. It's just a switch. It needs to be able to open this all the way on a 5 volt input, and that is actually uncommon. It is normal for them to need way more voltage, say 12 volts or more, to fully open this switch. If you buy some random one and power it with 5 volt, it will open the gate. So you'll think it's working. However, it will only open this gate a small amount, and that can result in significant heating. The rest can be lost as heat, and boom. So there's quite a lot of MOSFET systems that theoretically should be able to work with 300,000 amps, but in reality they don't, because you can't open the gate. The other one on that is that the actual leads can't realistically support the current that they actually say. And that's where a number of MOSFETs are more ideal, although you can't just wire them up in parallel. You have to use resistors, and it's more complicated using multiple MOSFETs. But that does depend on the load, of course. If it's not a huge TC, then this is the simplest and most cost-effective way. You also need resistors. It's not like you can just use a MOSFET with an Arduino. Now we're going to move on to radio-controlled speed controllers. Now this question comes up quite a lot. Can I use a brushed electronic speed controller, or can I use a brushless speed controller? Well, generally speaking, people they don't differentiate between a brushed one or a brushless one, and it's just, can I use a speed controller for it, electronic speed controller? And well, the answer is yes and no. That depends on what kind of speed controller you are using. If you're using a brushed speed controller, which is for old school motors, the answer is yes. And you could say this is the most successful way of controlling a TEC's voltage, because they're an all-in-one solution. They're built for huge amps, so use one of those. So they have a brushed speed controller, has 2 inputs and 2 outputs. This is the power in, goes to your battery, and this is the voltage / power out. Now on a brushless speed controller, you have power in, which is 2 wires, and power out, which is 3 wires. So coming back to 2 wires and the brushed speed controller, this can't work by itself. It needs like a servo tester, which needs to plug into the servo, and you can buy one of those for like $2. Then sure enough, you can control the power going to your TEC with one of these and a servo tester. Done, and it will work. Now, the important thing to know is that you need to make sure you buy a brushed speed controller that can handle the input voltage. The majority of these are for remote control cars, and they're normally about 2S or 8.4 voltage. If you want 12 volts, then you need to go to a 3S or more, so you need to make sure that it can handle the input voltage. The important thing, well, it's not that important to be honest, but it is a factor, is the speed at which this, and this goes for the MOSFET as well, how fast it turns the power on and off. The faster the better, to reduce the thermal cycling that we talked about before. Generally it's in the thousands, so whereas when we talked about the PID, you were turning it off every 30 seconds, probably more, could be minutes, could be days. This will be happening many times a second. So the higher the frequency, the better. However, the higher the frequency should result in more thermal losses because it's having to switch more often. So if it's getting hot when it comes to the MOSFET, reducing the frequency will reduce that. But you want to keep that up as high as you can. With a MOSFET, you can adjust that based on what you're controlling it with. With a brushed EEC, you have no control over that. So you need to just have a look. But the reality is, it's the ones that I've seen, they're all fairly high frequencies. You don't really need to worry about it. But it is a consideration. Higher the frequency, theoretically you'll get a better efficiency. But how tangible the difference is, that's a debate. You could say by increasing the frequency of the MOSFET or the ESC will result in higher efficiency of the TEC but reduced efficiency of the speed controller itself, so total efficiency may be similar-ish. But anyway, you can use a brushed electronic speed controller either controlled by a servo tester, or you can control it by a Arduino, which is what I would do, because then you can then connect some kind of thermal probe. But if you're not interested in the thermal probe, then you can just control this with a servo tester. The outputs then you obviously connect to your TEC and inputs to your power source. Now, brushless EECs unfortunately are a different ball game. They have 3 output wires, and you cannot use them to power a 2-wire TEC. Now, the very pedantic person out there will say, yes, you can just add some rectifying diodes and we can turn this into a 2-phase system, blah, 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 blah. Well, yes, you can. But for the normal person that's not crazy, awesomely ninja at electronics, I won't be able to do that, so don't bother. So don't bother with brushless ESCs. These are kind of now the most common on the internet, largely because of drones, which tend to use brushless motors because they're greater efficiency. But the easiest way to tell, if it's got 3 wires out, it's a brushless motor, you can't use it. If it's got 2, you can use it. So that's my kind of rough guide of trying to control the power going to your TEC from existing hardware you can just buy off the internet. Which ones you can use, what are the pros and cons of them, and that's pretty much it. So hopefully you'll be able to power your TECs with this information and you'll get the results that you want. Hopefully you've enjoyed this one. Subscribe if you like this information. Subscribe if you don't like this information. But something tells me you're already not here if you don't like this information. I'll see you on the next one, guys. Bye-bye.